Good evening, everyone. So, we are here to discuss the assignment number 11 of this NPTEL course, Symmetry and Group Theory, which is taken by Professor Anindya Datta. I'm Shruti. I'm a PMRF scholar in the same department at IIT Bombay. So, let's start. So, in the week 11th assignment, the first question is LCAO is a level of theory used in this course because now LCAO is linear combination of atomic orbitals. Now the answer is very simple and the answer is simple itself. LCAO linear combination of atomic orbitals. So we are using this because it is very simple to apply and we don't need to solve the Schrodinger equation, and we cannot solve actually Schrodinger equation for molecules. It is all only solvable for hydrogenic systems and molecules are much bigger. So that's why we are not using that approach and we are using this combination of atomic orbitals as an approximation to form molecular orbitals. So the answer is first one, that LCAO is simple, that's why we are using it. Now the next question is, for a LCAO MO, psi of k is equals to summation I Cik phi I, not using Huckel approximation. So when you use so psi of k is a molecular orbital. Is a molecular orbital and it has been formed by some linear combination of phi I. Phi i's are atomic orbitals. Atomic orbitals of different or same atoms depending upon the molecule. So for if we are not using Huckel approximation, then we know that because of the orthonormality of the atomic orbitals of an atom, the this integral is equal to 1 because of the normalization due to normalization condition and due to orthogonality, this is equals to 0. So psi 1 and psi 2 of the same atom are orthogonal to each other. Orthogonality condition. Okay, so answer to this question is the first one and the second one. It is asking when we are not using Huckel approximation. So if we are using Huckel approximation, what will happen? So when you are using Huckel approximation, it will be the, so this integral psi 1 is written as HII. Okay, it may be psi 2, psi 2, or it may be psi 3, psi 3. So in general, it is written as like this, HII, and this integral between different atomic orbitals is written as Hij. Now, when we are using LCAO, means the atomic orbitals can be from the same atom or from the different atom. So here HII is written as alpha and Hij is written as beta. So this is using Huckel approximation. But when this approximation is not used, this integral is equals to 1 and this is equals to 0. And and this is equals to, yeah, that's it. So here answer is psi 1, psi 2 equals to, the integral equals to 0 between different atomic orbitals of the same atom, because it is saying not using Huckel approximation. Okay. So next is, in a system of linear equations with non-trivial solution. So non-trivial solution means it is not equal to 0. So if it is trivial solution means that determinant equals to 0. So non-trivial solution means that the secular determinant is not equal to 0. And this is true for any determinant, not in this case of molecules. For any, in general, from mathematics concept, we say non-trivial solution means that determinant of the matrix is not equal to 0, and for trivial solution it is equal to 0. So here the answer is D, not equal to 0. Okay. Again here the question fourth is about Huckel approximation. So the Huckel approximation says Sij equals to 0, Hij equals to 0 always, Hij is not equal to 0, and Hii is not equal to 0. So what I told, this is a single answer question, it's not multiple select, so we need to choose the best answer. Now what I told is Hii is equals to alpha, Hij is not equal to 0 always, uh, Hij is equals to 0 always. So it is also not true, because Hij is equals to beta, and Hij always condition is not true. It will depend upon the molecule we are considering. But Sij is always equal to 0. Now Sij is overlap integral. So Sij is equals to overlap integral. So Sii is equals to 1, overlap between the atomic orbitals of same atom, and Sij is overlap integral. So they say that this overlap integral is equals to 0 unless I and j are unless I and j are adjacent to each other. Okay, so this is if they are not adjacent, we will write overlap integral some value s. Okay, so for this question, the correct answer is A. Sij is equals to 0 between the overlap orbital between the atoms which are not adjacent, so far apart atoms. Okay, now the question 5 is about a fully rotational subgroup can be used to construct the PSALCs for an aromatic molecule. Now P is pi MOs for an aromatic molecule only when, so the answer to this question is the rotational subgroup can be used, for example, instead of D4H you can use C4, instead of C3V you can use C3, like that. So if such rotational subgroups can be used only if the group subgroup relation is 1 to 1. One-to-one character mapping should be there. Okay, then only we can use, so we can use the projection operator on the elements of C4 that will reflect the behavior in case when we will take the full point group, which is D4H. So only when the group subgroup relation is 1 to 1 we can use this rotational subgroup for like smaller point group for a bigger molecule. Okay, now for a cyclic, next question is for the cyclic C3H3 plus ion, the lowest energy molecular orbital has symmetry and energy respectively. Okay, so this question has been done in the class where the symmetry we had find, which was, I think, so the symmetry was A, I guess. Yes, so the symmetry was A, but we didn't calculate the exact energy in terms of alpha and beta. So let's first calculate the energy and then we can derive the symmetry again. So cyclopropanol, the molecule looks like this with a positive charge here, here 1H, here 1H, and here 1H, C3H3 plus. Okay, so this point group is D3H actually. So when we'll write the secular determinant will look like, so the secular determinant will look like H11 minus ES11. Let's name these atoms as 1, 2, 3. H12 minus ES12, H13 minus ES13, H. So there are 3 atoms, so it will be, the secular determinant will be a 3 cross 3 matrix. H22 minus ES22, H23 minus ES23, H31 minus ES31, H32 minus ES32, H33 minus ES33. Okay, so this is a secular determinant. This will be equal to 0. Now let's see what are the values of this H and S. Now, since the molecule is like this is 1, this is 2, this is 3, here a positive charge is there. So for the same atom, interaction energy, interaction term will be 1. So H11 interaction term will be alpha, not 1. H11, H22 and H33, because this is the same interaction with itself, so it is equals to alpha. And H12, H21 equals to beta, H13, H31 equals to beta, and so on. So H23 equals to H32 equals to beta. So I can write it like Hij equals to beta for I not equal to j. Okay, and similarly the overlap integral Sii will be equal to 1. Sii means S11, S22 and S33. So this is S11, S22, S33. So this means overlap with itself, and Sij will be equal to 0. This is the Huckel approximation. Okay, so let's put these values. So when we'll put these values in the secular determinant, it will be alpha minus E, beta, 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 alpha minus E, beta, 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 alpha minus E equal to 0. So when, let me write it like this, alpha minus E by beta 1, 1, 1, alpha minus E by beta 1, 1, 1, alpha minus E by beta. So this is the same thing. I am just dividing this determinant by beta. Okay, so let us take x is equals to alpha minus E by beta. Then this determinant will become x11, 1x1, 1x. This is equal to 0. This is just for simplification. So when I am solving this determinant, it will be x square minus 1 . So on expansion, it will be x cube minus x plus 1 minus x equals to 0, which means it is x cube minus 3x plus 2 equals to 0. Now one of the root, this we got a cubic equation. Now one of the root will be x is equals to 1. So when we'll put 1 minus 3 plus 2 will be equal to 0, will satisfy this. So one root is x is equals to 1. The other root we can find by simply dividing it like this, x cube minus 3x plus 2 So we need to put here x square, this will be x cube, sorry, it will be minus x square. On minus, this will become plus, this will go. So we are left with x square minus 3x plus 2. Next term I'll put plus x. So this will be x square minus x. So on dividing it will be this will go. This will be minus 2x plus 2 and minus 2 will satisfy this. So the two roots are like this, x square plus x minus 2 equals to 0. Then on simplifying this, it will be x minus 1. This also will break into x minus 1, x plus 2 equal to 0. Okay, so the values of x we got 1, 1, minus 2. X was equals to alpha minus e by beta. It implies e is equals to alpha minus x times beta. So when I'm putting x equals to 1, it will be alpha minus beta. Again x is equals to 1. So second energy, it is alpha minus beta. And then when I'm putting x is equals to 2 minus 2, it will be alpha plus 2 beta. Now beta is negative. So since beta is negative, let's take beta equals to minus 1, or not minus 1, let's take beta something negative. Then this term will be of lowest energy, and these two terms, these two energies will rise up. So when beta is negative, these two will have same energy, alpha minus beta, and this will have the lowest energy. Since beta is negative, this term will become alpha minus 2 times something, and we are subtracting something from alpha, and here we are adding. So this will become the lowest energy, alpha plus 2 beta. Okay, so the lowest energy is alpha plus 2 beta. So answer to this question is alpha plus 2 beta and A. Now, how we got the symmetry? Symmetry is found by using the projection operators. That we did in class. I'll show you again. So for this, now when we will write this molecule, the pi orbitals, so this is 1, 2, 3. Okay, means phi 1, phi 2 and phi 3 denotes p orbitals of carbon 1, 2 and 3. Okay, so here the point group is D3H. So let's see how the irreducible representation is. So in D3H it is E, 2C3, 3C2, sigma H, 2S3, 3 sigma V. Okay, let me name this as gamma 5. Phi is the p orbital. So under E there will be no change. So it will be equal to 3. Under C3 all will change position, so it will be 0. Under C2 the atom through which the C2 is passing, that will not change, the other two will swap their position. So under C2 the character will be -1, minus because the p orbital will change their lobes. Sigma h -3 because the p orbitals will change their lobes, but the positions will not change. Now S3 will be 0 and sigma v will be 1 because the plane, the atom through which the plane will be passing will undergo no change, but the other two atoms will change their places, so they will swap. But here sign will be positive only because it is a plane, not the rotation. Okay, so when we, this is the irreducible representation. So when we break this reducible representation into linear combination of irreducible representations using the great orthogonality theorem formula, it comes as a2 dash, it comes as a2 double dash plus e double dash. So this is one dimension, this is two dimensions, total three dimensional we get. Now when we apply, now when we apply projection operator, now we can work with, instead of D3H, we can work with the cyclic group C3. So when we apply the projection operator of asymmetry on phi 1, what we get is phi 1 plus chi, epsilon phi 3 plus epsilon star phi 2. And when we apply, this will come for E. For A, it is a totally symmetric representation. We will get phi 1 plus phi 2 plus phi 3. And when we apply this for E, we get phi 1 plus epsilon plus epsilon star. And the other E, when we will apply, so this is 1, this is 2. The other E symmetry, when we are applying it on phi 1, we get phi 1 plus epsilon star phi 3 plus epsilon phi 2. This we name at equation 3. Now this phi 1 projection operator of E1 and E2, so these contain imaginary terms. So to remove them, what we will do, we will add ones and subtract ones. So when we'll add, we'll get this 2 phi 1 and also epsilon plus epsilon star is equals to -1. So we will get, let me write, linear combination E1 dash will be equal to phi 1 minus phi 2, 2 phi 1 minus phi 2, phi 1 plus phi 2, this epsilon star plus epsilon will be -1, so it is minus phi 2, and this again is -1, so it is minus phi 3. One linear combination is this, and the normalization constant will be 1 by root 6. Considering this, 2 square is 4 plus 1 plus 1, 6. Now this combination is upon addition. So when we'll subtract ones, so on subtracting we will get psi 1 will get cancelled out. This one will be psi 1 epsilon minus epsilon star, and this will be epsilon star minus epsilon, and we can divide by I to get the real component. So it will be psi e1 double dash, let's keep its name as e2. This will be phi 2 minus phi 3, and normalization constant will be 1 over root 2. Okay, now this means that we have got 3 molecular orbitals now. This means that psi 2 and psi 3. So psi 2 is positive. There is nothing at psi 1. Psi 2 is positive. Psi 3 is negative. And there is one node here. Okay. Number of node equal to 1. Now for psi e2 double dash, this combination we have, this is positive, these two are negative, and psi 1 is twice the magnitude. So this will be, so this is positive but bigger, this is negative, this is negative. So there is a node here. Number of node is equals to 1, and psi a2 double dash is the totally symmetric one, means all positive with magnitude 1. So here node is equals to 0. So the one which has lesser number of nodes, or the least number of nodes, is said to be the lowest energy. So this is here of the lowest energy. Okay, so we have found out the lowest energy symmetry belongs to A2 double dash, or when we are writing in terms of molecular orbitals, we will write it as A2. Hence, to answer this question completely, first we figured out the energy, which is A plus 2 beta, and the symmetry is A. So the answer is fourth one here. Okay. Now this question, for tetramethylene cyclobutane, the SALC has a symmetry. So let me get a character table here. This is D4H and we will need C4. This Okay, so the actual molecule, this molecule shown here, has a point group of D4H. But instead of figuring out all these symmetry operations, we can just figure out the rotational subgroup, which is C4 for this. So that's why I've kept the character table of C4 here. Now let's see, we need to figure out the symmetry of this SALC. Now phi 2 minus phi 3 is this one. So phi 2 will be like this. Suppose this is the positive phase and this is, psi 3 is negative. So here the positive phase is downside. This is psi 2, this is psi 3. Now we can figure out the characters, how they will change, and then we can figure out the symmetry corresponding to those. Now under identity, the character will be one only because nothing will change. Under C4, C4 is here. So C4 will be passing from top like this. This point, this is C4. So when you will apply C4, there won't be any change of sign, but these will change place. So C2 will move from here to here and C3 will move from here to here, okay, by 90°. So let's say it will have no sign change, so the character will be positive, but it will change its place. Okay, so let's keep it like this till now. Now when we'll apply C2, what will happen? From here, it 180° it will change. So from here to here it will come. Sorry, C3 will come. So both of them will change place like this. C3 will be here, C2 will be here. Okay, and also there will be change of sign. So in case they will change sign. Yeah, simply they will come from. So here after applying C2, what will happen? We will get phi 3 here and phi 2 here. So here what will happen? They have changed their places. So phi 2 have so they have changed their places. So it is like now phi 3 minus phi 2. So the character should be -1 here. Okay. Next is C4 cube. When we'll apply C4 cube, first of all, they will change their place completely. So phi 2 will be here, phi 3 will be here, and there will be change of sign as well. So for C4, C4 cube, it will be so there will be change of sign. So C4 means negative rotation. So psi2 will come here. This will be phi 2 and this will be phi 3 down. Now the lobes have got changed, so it will be negative, and they have changed their places, so it will be some number. The character cannot be +1 or -1 here because they have changed their places. So when we are comparing this with the representations in the C4 point group, so we can see it is matching corresponding to E, the first one. 1, positive, -1 and negative. The complex number is because they are changing their places. Okay, so we can say that it is of symmetry EA, the first one. If this is EA, this is EB, then we can say that phi 2 minus phi 3 is of symmetry EA. So that's how we can answer this. Or the other method is by using the projection operators, but that will be a lengthier method. So like this we can guess the symmetry of this easily. Okay. Now this question is again related to the same molecule, that for tetramethylene cyclobutane as shown above, the linear combination of SALCs phi 1, it should be psi 1 actually, this is psi 1 and this is psi 2. So psi 1 is equals to 1 over 2, 2, 3, 6, 7. Okay, 2, 3, 6, 7 means the inside ones. 2, 3, 6, 7. This is 1. This is 4. This is 5. This is 8. So these carbons, the double bond terminal carbons are 1, 4, 5 and 8. So they form a group 1, 4, 5, 8. Okay. Now this representation is, these two representations are totally symmetric representation. So it belongs to totally symmetric representation. Now the secular determinant will be H11 minus E, H12, H21, H22 minus E. Now these are not Huckel symbols yet. So how we will define H11? Because this is not yet a molecular orbital, it is SALC. So this is not corresponding to a, I mean this is not an atomic orbital. So H11 does not correspond to Huckel H11. So we have to convert it. Now H11 is defined as 1. 1 means we need to multiply this integral of this with H1. So it will be 1 by 2 into 1 by 2 will be 1 by 4. Then integral this is H11. Now psi 1 is equals to 2 plus 3 plus 6 plus 7. So it will be 7 H11, sorry, H only, interaction Hamiltonian, and then again psi 1. So phi 2, phi 3, phi 6, phi 7. So we will get 4 into 4, we will get 8 terms here, each multiplied by each. So actually we will get 16 terms, but others will vanish. So 2 when operated with 3 will give, because they are adjacent, they will give some value, but 2 when operated with 6 and 7, with 6 they will not give any value, with 7 it will give some value, so it will be like this. I will write with 1. Okay. Now if we'll do the same thing, we will get these 4 integrals only. So we will get all of this 4 times. So this will give alpha, this will give beta, this will give 0, this will give alpha, because these two are adjacent. Sorry, this will give beta. And when we will do this for, let's say, we will have more terms here, 12 more terms here, considering phi 3 with each, phi 6 with each, and phi 7 with each of them. So we will have total number of 16 terms, and each of the combination will give 1 alpha, 2 beta, and 1 term will be 0. So we will have 1 over 4 alpha plus 2 beta. How many times? 4 times from all 4 terms. So we will get H11 equals to alpha plus 2 beta. Now H22, similarly H22 will be 1 over 4. Now 1 over 4, psi 2 is 1, 4, 5 and 8. So phi 1, phi 4, phi 5, phi 8. Okay, so this is, again this will give 16 terms. Phi 1 H phi 1, okay, plus phi 1 H phi 4, plus phi 1 H phi 5, plus phi 1 H phi 8, and 12 more terms. So again it will give 16 terms, but this time, since this is same atomic orbital, so this is equals to alpha, but 1 and 4 they are far apart. So 1 and 4 are not adjacent. 1 and 5, 1 and 8, these are not adjacent. So these terms will be 0, 0, 0. So we will get 4 times alpha from each of the 4 sets. So here it will be 1 over 4 alpha into 4 from all the 16 terms. So this will be alpha. So H22 is equals to alpha. Similarly, when we'll do H21, this will be beta. H21 will be 1 over 4 psi2 H psi1. Now 1 over 4, we have seen psi2 is equals to 1 plus 4 plus 5 plus 8 H, and psi1 is equals to 2 plus 3 plus 6 plus 7. Now again this will give 16 terms, but this time all others will be 0 and we will be left with phi1 H, phi2. Since they are adjacent, phi1 and 1 and 2 are adjacent, so this value will be beta. This will be beta, and other 1 and 3 are not adjacent, 1 6 and 1 7 are not adjacent, so we will get 3 0 terms for one set, and similarly we will have 12 more terms like that. So in total we will have 4 beta terms. So it will be 1 over beta into 4. So H21 will be beta, and likewise H12 will also be equal to beta. So we have got now H11 is equals to alpha plus 2 beta, H12 equals to H21 is equals to beta, H22 is equals to alpha. So the secular determinant we can now write as H11 means alpha plus 2 beta minus E, H12 beta, H21 beta, H22 alpha minus E. So this is the secular determinant equals to 0. Now I can take beta common, so I will write alpha minus plus 2, 1, 1, alpha minus E by beta equals to 0. And let us take x is equals to alpha minus E by beta. So this will be x plus 2, 1, 1, x. So this is the shorthand notation, which means upon solving it will be x square plus 2x minus 1 equals to 0. So from here you can get the value of x by using the quadratic formula, plus minus under root b square minus 4 in, so it is plus divided by 2a, which is 2. Thus we get x is equals to minus 2 plus minus 2 root 2 divided by 2, which is minus 1 plus minus root 2. This is the value of x, not the value of energy. So energy was alpha minus E by beta is equals to x. So energy is equals to alpha minus x times beta. So it is E is equals to alpha minus x is minus 1 plus minus root 2 times beta. Now we have to write the energy in terms of beta. So we can put alpha equals to 0. So putting alpha equals to 0, so this is 0. Energy will be minus minus plus and plus minus will be minus plus root 2 beta. Thus the answer is energy in terms of beta is 1 plus minus root 2. Okay, so let's see which option. 1 plus minus root 2, not minus 1. This is the value of x. So answer is first one. This is the value of x. This is wrong, this is wrong. So here option 1 is correct. Okay. So there were 8 questions only here in this tutorial. So that's it for today. And there will be one more extra session and you guys will be notified about it somewhere before 23rd, before next Monday. Before the exams, there will be one last extra session where I will discuss the assignment of week 12. Okay, so that's it for today. Okay, so I'll close the session now.